morning. Today's topic for this video is SPLAY Trees. In today's session, we are going to see what is a SPLAY tree, what are SPLAY trees, different operations performed on SPLAY trees, comparison with balanced tree, and applications and advantages. So these are the topics we are going to cover in today's session, right? And first of all, before going to explanation with an example, let me say what is a SPLAY tree. The main property of a SPLAY tree is when you are going to search or access an element, the element what you are searching or whatever insert or delete has to be brought to the root node. So that is what we call, that element wherever it is, that has to be brought to the root. So that is what we call as splaying. This is actually a SPLAY tree is also a binary search tree. We already know what is a binary search tree. A binary search tree means the element which is left is less than the root node and the right is greater than the root node. That if the arrangements are like that, then we call that as a binary search tree. And many has a confusion whether the SPLAY tree is a balanced binary search tree. Actually, no, it is not a balanced binary search tree. It is just a self-adjusting binary search tree. So what is the self-adjusting binary search tree? That we will see when we come to this actual topic. And before going to that, we know what is a balanced tree. Balanced tree means a balance factor which should be either 1, -1 or 0. So that is what, if the balance factor is that, depending upon the levels, then it is called as a balanced binary search tree. In a balanced binary search tree, we have AVL tree and red-black tree. AVL tree is a strictly balanced binary search tree, but red-black tree is a roughly balanced binary search tree. Now coming to SPLAY trees, searching an element and splaying plus splaying, that is what we call as a SPLAY tree. This splaying, as I said already, the element what we are searching, that element has to be brought to the root node. Why it has to be brought to the root node means when you bring that element or the data to the search node, the access time is actually reduced. So that is the intention of this. When we come to the applications, I will say you why it is brought to the root node or where it is actually used in the real time applications, that we will see. Now coming to the operations of a SPLAY trees. As I said you, there are different operations that is done on a SPLAY tree to bring the root element, to bring the element what we are searching for as a root element. Okay, there are different operations like zig operation, zigzag operation and zigzag operations. So that is all we call as rotations. That is rotations we call that in the balanced tree, but here we call it as zig operation, zigzag operation and zigzag operations. That let me explain you with an example. Okay, now we have an example here. As I said, when you access an element, that element has to be brought to the root. Okay, the search element or the access element has to be brought to the root. So that is what is called as splaying, I said. Now we have an example here. So first is searching in binary search tree plus splaying. That is what we are going to do here. Okay, so searching in binary search tree, we know already how it is done. The element what we are searching for, or the key element, it will be compared with the root element. And if it is less, that is the key element what we are searching for, is less than the root, we go to the left hand side. And again we compare it with that element. And if it is again less, again left or right you go. So that is how we go in for searching. So that we know in the binary search tree. So same thing we'll do here, plus splaying will be done. Splaying, as I said you, the element what we are searching for, the accessing element, will be brought to the root by rotations. That is what is splaying. Now suppose if we want to search 12, okay, so search 12 means, how do you do this? You will compare the element 12 with the root element, that is 28, and 12 is less than 28, so automatically we will come to the left hand side. And here when you compare it with 12, that is the key element, so it is equal. So when it is matching, then you will bring that 12 or the search element. So searching is done now, you have found that element. So after searching, we go in for splaying. Search in BSD plus splaying is what we have to do. So once we identify the element, we have to bring that element to root position. That is what is called as playing, and then only the operation is over. So that is what is called as a SPLAY tree actually. So now when we search for 12, it is in the left side. So how do you bring this element to the root? So here, as we do in balanced binary search tree, here also we are going for rotations only. One right rotation, that is we have it in the left position, that is the element what we are searching is 12, that is found in the left position or left side subnode of root. It is actually a subnode of root. So that 12 has to be brought to the root node. So for this we go in for one rotation, that is right rotation, that is called a zig rotation. That is what we call a zig rotation. Same way, when we want to search for 42, which is the right subtree or right subnode of root, then again we go in for zig rotation only, but that will be done in the left position towards this side. Okay, so then that element will be brought to the root. So when the element what we are searching for is found in the subnode of root, only one rotation we do, that rotation is called as zig rotation. Either it can be left or it can be right. So that is called as zig rotation. So now if we do one rotation towards left or right, the element what we are searching has come to the root position. So your splaying is done now. So our intention is to bring the search element or the accessing element to the root position. That is what is called as splaying. So that is accomplished here. So this is what is splaying. So we will, when we want to rotate this or when we want to bring this 12 to the root position, what we do means one right side, I said, one right rotation like this we have to do. So for this, after that rotation is done, the tree will be like this. That is, 12 will come here, and your left node is 8 here actually, and your right node will be 28. That is, we have to see to that. How do you do it in a binary search tree? I mean a balanced binary search tree. Same way here also rotations is done. So here it is like this, and the node which is right towards 12, that is subnode of the node what we are rotating, has to be connected accordingly so that it satisfies the binary search tree property. That we already know that how it is done, that we have already seen in a balanced binary search tree. That is single rotation, how left rotation is done, how right rotation is done, how left rotation and right rotation, that and all we have seen already in the AVL trees. Okay, same way here also. So when we have an element or a right subtree of the search element, that has to be connected to the already existing root nodes left position. So that we will see here. Now here, after bringing the element 12 to the root position, your tree will appear like this. 28 here and 42, 70, here 36 and 65. So here this 14 will be your left subtree of this one, which is okay. So this will be your resultant tree after one rotation, one right rotation is done. So this is what you call as playing when the search element what you are searching for is the subnode of a root. Okay, one subnode of the, either it can be left subnode or right subnode of root. So after making one right rotation, that is we are searching for 12 and bringing that 12 to the root element or the root node. So your tree will appear like this after that right rotation. This type of rotation we call as zig rotation. This is called as zig rotation. So one right, it can be either in left side or the right side. So if you are searching for 42, then you will make a rotation towards right, left side. Okay, that again you call as a zig rotation. One rotation, that is one move from left to right or from right to left. That we call as a zig rotation. This can be done only when the search element what you are searching for is the subnode of the root. Then you will go for zig rotation. Now we saw zig rotation. So what till now we have seen what are SPLAY trees, different operations. Zig rotation we have already saw, and we are going to see what is the zig rotation. Come to zig rotation. When the search element, with the same example I am going to say about what is zig rotation. Now when the search element is 8, that is the left child of the root and again the left child of the root, or the right child of the root or again the right child of the root. So when we search for 8 or 70, okay, what will be the rotation, or how you will bring that element to the root is actually we will again do one left rotation like this and one right rotation like this. That is not one actually, 2. We will bring this here, again from here to here. So 2 left rotation and 2 right rotation. Okay, 2 right rotation, sorry, left rotation and 2 right rotation. So that is what you call as zig rotation. So when do you go for zig rotation means the search element or the element what we are accessing is the grandchild of the root, is the grandchild. It can be either left grandchild or right grandchild. Okay, not left it should be left or right. It should not be left and right left also. That is not possible for a zig rotation. For a zig rotation, you will go for 2 left rotations or 2 right rotations. That is, when we search for 8 or when we search for 70, we go in for either zig rotation or again left towards left or towards right. That is what we call as zig rotation. So how do you do this? This also we already seen in the balance binary search tree. For balancing, this type of rotations we do when the particular node is not balanced. As per the balance, how do you find it means we already know balance factor should be less than 1. It should be less than, not less than 2 actually, 1, 0 or minus 1. That is what is balance factor. So same way here also 2 left rotations or 2 right rotations. Now suppose when we are searching the element, the searching element is 8, how do you perform 2 right rotation? How do you perform 2 right rotation? So after doing 2 right rotation, your tree will be like this. The root element. So first of all, when we do 1 right rotation, it will be like this. That is 28, and this will be 8 actually, and here 1 right rotation like this. This is 12, and again you have 14, and this side nothing will happen, so it is 42, and same thing 36, 70, and you have 65. So this is 1 right rotation we have done, 1 right rotation. Right? 1 right rotation. We are bringing the 8 to the root. So 1 right rotation. After this, again 1 more right rotation. So that is what we call as zig rotation. That is what we call as zig rotation. Either 2 right or 2 left rotations. So after doing the second right rotation, your tree or the element what we are searching for, that is 8, will come to the root position. After that rotation, your tree will appear as, okay, 1 right rotation we have already done. Next, I have to bring this 8 again to the root. Then only SPLAYing is done. So we are bringing 8 to the root again. So 8 will be in the root, and there are no left nodes here. Same way here also no left nodes. Suppose if we have 2 here, this 2 will be here also. Suppose if we have 2 here, we will have the 12 here, 2 here also. And if we rotate again, this 8 will be there and 1 left node will be there, that is 2. And all elements will be in the right side. So we have to satisfy the BST property, binary search tree property. So this 12 is right of 8. So when it is right of 8 here, there also it should be right of 8 only. So that is 12. That is 12 there. And 14, where will the 14 go? When we go in for a left right rotation or right left rotation, this will actually get the position of the, this node's left position, that I will say here. So you will have again 28. This is the root node, and now this 14 will come here. This 14 will come here, and the rest of the elements will be same as it is. 42, 36 here, 70, and finally we have 65 at the left position. So this is how your tree will appear after zigzag rotation, that is bringing the grandchild of root node, left grandchild of root node to the root. So this is the actual. When we see this node, it is not a balanced binary search tree. It is just a SPLAY tree, that's all. So that is why I said you it is binary, SPLAY trees are not balanced binary search tree. It is a self-adjusting binary search tree. So it will adjust itself, make rotation, and bring the element what we are searching for to the root. That is what is SPLAY trees. They are not balanced binary search tree. When we see here, the balance factor of 8 is more than 1 actually. So that cannot be there for a balanced binary search tree. So again, balanced binary search tree is different and SPLAY trees are different. Always SPLAY trees are binary search trees, but they are not balanced binary search trees. So this is about zigzag rotation. Now next is zigzag rotation. For the same example, we will see how zigzag rotation is done. So now zigzag rotation. Suppose the search element is 14. Okay, the 14 is actually in the position from root, it is left subchild and then the right subchild of the subnode. So that there the 14 is here. So in this case, we go in for one left rotation and then one right rotation. So that is what we will do here. So this type of rotations, then you call that as zigzag rotation, zigzag. So the element, suppose the element what we are going to find is U, that is, this is U means, this is parent of U and this is grandparent of U. So the element what we are going to find is left child of root and right child of parent. Okay, then you will go in for zigzag rotation. In previous case, it was zigzag rotation, that is the element what we are going to find, or the element is in the direction of left of root or right of root. That is, the element is the grandchild of the root in left direction, or the element what we are going to find is the grandchild of root in right direction. We go in for zigzag rotation. Now in this case, we go in for zigzag rotation, where the element what you are finding, that is U, is in left and right direction of the root. So this is U means this is parent of U, this is grandparent of U. So it is here left direction and then you have it in the right direction. So here it is two rotations we are going to do. One is the zig rotation, other one is the zag rotation. So one towards left side, other one towards the right side. So when we do one left rotations, when one left rotation is done means you will bring this 14 to this position, and from here you will do again one right rotation and you will move the element to the root position. So search 14. So after one rotation, that is one left rotation, your tree will be 28, 14, and then here your 12 will be here, and then 8. Again you will have 2 here. Now, so this is how after one rotation, that is bringing and then 36 and then 70 and then 65. Now again we have to go in for one more rotation, that is right rotation, right? So that how do you do means one right rotation towards this side. This one we have already seen in the balanced binary search tree with AVL trees and red black trees. So now 14 will come to the root, and your left side there is no change. 12, 8 and 2, and here your 14 will go there, and your 28 will be your right node, and there is no other change. 42 here, left is 36, right side you have 70, and again right side you have, left side you have 65. So after zigzag rotation, your tree will appear like this. After zigzag rotation, that is bringing this node to the root position. So this is what we call as zigzag rotation. Now, next thing is a comparison with balanced trees. As I said you, when you compare it with balanced tree, SPLAY trees are not actually a balanced tree. Balanced trees are AVL and red black trees only. SPLAY trees are not balanced binary search tree. Okay, so that is also over. Now coming to the applications and advantages. Now, SPLAY trees can be easily remembered by using this few steps, or you can say it as an algorithm also. When you see here the SPLAY trees, while u not equal to root, u is the element what you are searching for. If it is not equal to root, then you have to check for this, that is, if u has no grandparent, do zig operation. If it is equal to root, then you will get exit. You will actually exit and you will come out, because the element what you are searching for is in the root position. So you don't do any splaying or anything, you just come out. When the element what you are searching for is not in the root, then you have to check whether if u has no grandparent, then do zig operation. What does that mean? If the u means the element what you are searching for has no grandparent. Suppose this is the element what you are searching for, then this will be the u. This does not have grandparent. Only parent is there, no grandparent. So if u has no grandparent, do zig operation. That is what I already said. Only it can be either left child or right child. Then you do only one left rotation or one right rotation, that is zig, that is do. Else, otherwise, if it is not that, the element what you are searching for is not the left or right child of root. If direction from GU to PU, that is grandparent and parent, is equal to direction from parent to U, that is left or right. Here you can see here, if direction from grandparent to parent is equal to direction from parent to the element what you are searching for, PU to U, then do zig operation. So here you will go in for two left right operation, or two left operation, that is zig. Else do zigzag. So if it is not the left child, or if it is not the right child, if it is not the grandchild of left or right, then we go in for zigzag. That is this one or this one. Then we do zigzag and come out. So these steps will help you to easily remember how splaying is done, how the root element is brought to the root position. Now coming to the time complexity of the SPLAY trees. Coming to the time complexity of SPLAY trees, let's take an example. One example like this, when we have 15, 18, 20, 40, something like this. So you have a SPLAY tree like this. This is also a SPLAY tree. It is a binary search tree. You can say this as a skewed binary search tree also. Now, the time complexity here for the SPLAY tree, if we go in for the element, that is what we are searching for is 40. Suppose we are just taking it for an example. The element what we are searching is 40. Then the time complexity will be order of n. Why? Because we will compare it with the root element. That is the element what we are searching for is 40. Will be compared with the root. It is not matching. If 40 is greater, you will come right side. Again, it is not matching. You will come again right side. Now you have found here. So n comparisons you have made. N comparisons from the root to the search element is done. But once you search, you will automatically go in for splaying. Splaying means you will bring this 40 to the root position. This position. You will bring this root. So the SPLAY trees are mainly useful when a particular data or when a particular element is accessed frequently. When it is accessed frequently, that is what you search once 40, once search is done, you splay it and bring it to root position. Then again you want to use the same data 40 with that element again you search. And in the second condition or second time when you search or second time when you use the data will be in the root position. So here the order of, the time complexity of searching that element will be 1, just 1, because at first comparison itself you have found that element and it is 1 now. So the time complexity of the SPLAY trees will be order of log n, because it will be order of log n because as at first operation or first accessing the element it will be n, and in frequent operations when we search for the same element or when we use the same element, then we search for the same element, those times and all it will be only 1 because splaying is done, that element is brought to the root and it is easier to access the element frequently. So SPLAY trees are mainly used when the particular data is used frequently, or when the same data is used frequently in different operations, we go in for SPLAY trees. That is what I can say with applications or advantages of SPLAY trees. So this is the time complexity. So order of n at first time, and when we go in for n number of operations, it is actually changing and it becomes to order of log n, because at first time it is n and the next time and all it is just 1. When we use n times, it is always the 1 only, because we have brought that element to the root position. So this is how the splaying is useful, and main applications in real time is when you take a cache memory. The cache memory concept, in the cache memory concept, the data, it is using this concept of SPLAY trees only. So we know what is actually a cache memory. In a cache memory, the data what we are using frequently will be in the cache, so that the accessing time of the data will be less and your time complexity is good there. So that is why we are going for a cache. This is fast memory, you can say, where the data which is used frequently will be stored there. So in cache memory also this concept of SPLAY trees are used. So that is one application. And some other applications also, if you want to send from source to destination one data, the same two machines are frequently accessing the data, then there also you can say that SPLAY trees concepts are used, where the same number of operation increases with the same data, then SPLAY trees are the good example, or you can say that concept will help you more to increase the time complexity. Thank you.